And now we've reached the end. The culmination of all of these thermodynamics videos results in a calculation of what a human looks like. More precisely, what the average and most probable photon frequencies of a human are as a result of their temperature. So we're given Lars. We're looking at Lars, whose body temperature is 310 Kelvin. We're going to assume that he's a perfect thermal emitter. Not quite true, but it's an okay assumption for now. What we're interested in, if we have the electromagnetic spectrum here, where frequency increases to the left, that's the way it's usually drawn. So you go from radio waves to gamma rays passing through visible, the stuff we can see as you increase in energy and frequency. This is the little chunk that we can see right here. We just want to know where the peak frequencies for Lars are, both the average and the most probable photon frequencies. So we can figure that out now. And we do that using the results quoted in your lecture notes, namely that E bar is 3.83 kT, and that the relationship between the energy and frequency of a photon is E equals hf, where h is Planck's constant, named after the same Planck for whom the distribution function is named. So if that's true for any photon frequency and energy, it must be true for E bar and what I've called F bar, that'll be the average photon frequency. So we can solve for F bar. F bar is just 3.83 kT divided by h, and we can put in those values. We insert the value for K, the temperature is 310 Kelvin, we put in the value for Planck's constant. We get out that F bar is 247 times 10 to the 12th hertz. Okay, frequencies are measured in hertz, that's a really high frequency. Let's measure it in terahertz, which is 1 times 10 to the 12th hertz, so the average frequency is 247 terahertz. If you look at the rainbow to the left, you can see that the visible spectrum ranges from 430 terahertz to 750 terahertz, so we're to the right of that. That means that we're somewhere over here in the infrared, and I didn't try to draw it scaling too accurately, but that means that Lars's body temperature, the average photon frequency, is in the infrared. Maybe not surprising, if you turn off the lights you can't see Lars unless you have an infrared camera. Next step is to compute the most probable photon frequency. Well, Fp is just Ep over h, and we know from our lecture notes that Ep is 2.82 times kT. You could go through and put in the values for K and H again, or you could just take a ratio. Ep over E bar is just 2.82 divided by 3.83, the kTs will cancel, so that's kind of nice. We can just say that Ep is 0.7363 E bar. We know that the frequency at which the peak occurs is 0.7363 E bar over h. That means that the peak frequency has to be 0.7363 times the average frequency. Well, we just computed the average frequency. It was 247 terahertz. That tells us that the peak frequency is 182 terahertz, also in the infrared. So Lars's thermal emission comfortably sits in the infrared. If you look at him with an infrared camera, you can see him. Otherwise, you don't see any visible emission. The distribution function probability for finding visible emission from Lars at 310 Kelvin is very low indeed, far too low to be detectable by the human eye.